Good morning, everyone. How are we all? I have the where is it? Lecturer in charge here with us as usual this morning. It's been a very unusually chilly spring here in Sydney, so someone just likes sitting wherever it's warm, which is potentially just on my lap while I'm talking. And just make sure my camera is all set up. Yes. Good to go. Okay. So today we are approaching the kind of pointy end. I think I said this last week anyway. The pointy end of COMP1511, because we've kind of built all of the big structures that we're going to for the course. This week I'm talking about things that are kind of extensions on what we've learnt already. What I'm going to talk about today is extending the ideas that we put together with multi-file projects. And I've really kind of introduced this topic already, but we're going to go deeper into it. And the topic is one called abstract data types, which is the capability to work with multiple files and utilizing the fact that if you have these kind of multiple file projects where you're including the header file but not necessarily the C file, so it's all compiled together, but the files don't necessarily see exactly what's inside the other files, we can build up a situation where you can use some of what you can see but not all of it, which then allows us to protect some of the data that we're using and also constrain how we use things so that we can make sure we follow rules. And so today we're going to look at one set of rules that we can use to put something together, and a particular example which hopefully once I show you the way it works will become familiar to you. These are called stacks. They're not the only form of this abstract data type, but they're one of the most common. And on Friday, I'm going to show you, I'm going to introduce you to this wild and inverted way of programming called recursion. Recursion is like, it's nearly thinking about programming backwards in a sense. Mathematics has been using it for, I want to say thousands of years. I don't know if it's thousands of years. It's definitely at least hundreds of years. So it's not new to humanity at all, but it might be new to you in programming because a lot of the programming we've done up until this point has been very step by step. We follow line by line by line, but when we do recursion, we follow this kind of inverted idea that we think about how it finishes first and then wind it backwards kind of through how it works. It's hard to really describe it, but we'll talk about that on Friday. I hope everyone's going well with their assignment 2 at the moment. Same reminders I give all the time about assignments. There's the old proverb, the best time to plant a tree is 50 years ago. The second best time to plant a tree is right now. So if you haven't started yet, I would suggest, even if you haven't started and you don't really have time to start it yet, at least read the spec. So put aside just like half an hour, even if you don't have time to really work on it. Read the spec, have a look at it, and allow it to kind of settle in your brain. And that way, when you start doing it, there will be some ideas partially formed in your head, so you don't go in cold when you finally do get to start it. Another thing is that all of the kind of structures to help you with the assignment are in place at the moment. So one of the best places to get help is to go into a lab, and it doesn't have to be your lab. It can be any of the scheduled labs. You can check out the timetable on our WebCMS page. You can also go to Blackboard Collaborate, which is the system you've been using for all of your tutes and labs, and see what other tutes and labs are running. I've spoken to the tutors already and let them know that they may have visitors coming in during during other, during their lab time, visitors who aren't necessarily enrolled in their lab, and if they've got some spare time, they could help them if they can. So there's that kind of support. There's also help sessions running. The help session timetable is available on the course website. And failing that, there's the forum. Forum is not quite as good for personal help because you have to ask a question and wait. Whereas if you have one-on-one help, you can ask a question, talk about it, then ask another question and things like that. Raman's asking, is the testing part of the assignment as long as the stages? No, it's definitely not. You're not going to be writing as much for the testing. Also, you don't have to think about how the program's going to solve the problems when you're testing. When you're testing, it's just a matter of saying, looking at the inputs and the outputs, what should they be? So you can think about how the program ought to run if it runs correctly, and just test for that. So once you've written a couple of tests, the rest of them are actually pretty easy. They should fall over once you've figured out the method for testing, which is really what that's about. That's why it's only worth 10% in the assignment, is trying to get you to a point where you're okay with the idea of how you set up tests and how you build them. Gira-chan saying, Spotify.h file says playlists have the digits in them. Oh, that have digits in them are invalid. But 1511 Spotify treats names with digits as valid. Oh, you're saying no, you read it wrong. I thought digits were okay, but spaces and other characters are invalid. I would have to check on that. There's lots of little details like that Tammy has made those kind of line call decisions on exactly what is and isn't happening in those little details. Okay, so let's get into the lecture for today. What did we learn last week? Yes, as Gira-chan and Answer are saying, digits are okay. I got to put my face in here. Just like, wait, which way is the arm? Linked lists. Okay, that's my meme for the week. So last week we finished linked lists in that we looked at pretty much every operation that we might do with linked lists, at least in their simplest basic case. So we looked at creating lists, we looked at inserting into lists, but not just inserting. We looked at finding a particular place in the list to insert into. We looked at removing from lists, and we looked also at finding a particular node to remove, and we wrote a function that was going to clean up all the memory of the linked lists. So I think that with that, we have all of the basic tools necessary to do full manipulation of linked lists. We can insert anywhere into the list, we can remove anywhere from the list. We have multiple ways of searching through the list to find something. We have ways of looping through the list and just performing an operation at every element. We have memory allocation, and we have memory freeing. So over the course of those 3 lectures, we put together everything I think we needed to for it. David, sorry, this question there saying, is it okay if the program returns an accessing a field using a null pointer if someone tries to print the library after the library has been deleted? Yeah, I'm pretty sure that the reference solution has been changed now. I think Tammy's already put that change in, because we noticed that in the live stream that we did it, that if the library has been deleted, pretty much the only valid operation after that from the main is to quit the program. Because if the library's been deleted, it's finished, it's over. Because the only time we'd create a library would be at the startup of the program. And so basically, to delete a library, the idea is that you're deleting just as you're going to finish using things. Okay, so hopefully everyone's got a decent idea of what's going on with linked lists. If you don't have a full idea of what's going on, you can still spend some time with it. You can go back over them and have a look. I'm actually going to use linked lists a little bit today, but not necessarily in a way that's going to teach you how they work quite as well as the last few lectures. So if you're still worried about how linked lists work, it's a good time to sort of go back over things. Your tutorials and labs this week are going to work on linked lists again, so hopefully if you're having some trouble, you can talk to your tutor about it and get a bit of one-on-one help. Gira-chan, Spotify, a local music streaming service that does not stream any music. We actually had an idea to write some code for you to attach Spotify to your to the actual Spotify library, because Spotify has a web API where you can play songs. So we were thinking of adding this code to the assignment so that you could actually use the playlist that you're creating in the program to hook up to Spotify itself, but it ended up being a choice between polishing the assignment to make sure it was nice on release, or adding these features, which were kind of just fluff, but not necessarily teaching you about programming and stuff, so we left it out. But, you know, there's actually a possibility. You could consider, if you want to do some Hall of Fame stuff, for Spotify to actually store the Spotify's URIs, so they've got links that you can link to directly to songs in Spotify, and you could actually print those out and say, if you click on this, it would do something. Not that clicking on text in a terminal is automatically going to go open a hyperlink, but you could take one step in that direction if you wanted. I don't think there's actually a Hall of Fame. I don't know if we've actually set up Hall of Fame for this one or not, but, you know, challenges are fun no matter what. Okay, so what we are talking about today, we are doing abstract data types, and we're going to do a recap of what we were talking about with multiple file projects. But as I do that recap, I'm going to add new detail in. So I'm going to talk about how exactly these things are working. I think it's actually going to be, there's not actually much new information, but it's more how we're thinking about it. And then we're going to do an example that shows how we might implement an abstract data type with a stack. And what I'm going to try to do, and it depends on time, is I'm going to try to implement the stack using linked lists and also implement another stack using arrays. I probably won't get to finish the arrays one, but I've got a lot of slides in here you can look at if you want to. But what I want to show is that the idea of abstract data types allows multiple different implementations to still work without having to change any of the other code, so long as the implementations follow the recipe given in the H file. So let's get into it. Have a look at our recap and build up this idea. So when we were doing multiple file projects, we looked at separating code into header files and implementation files. So every section of things that we were working on. So Spotify is a great one because you can see that the main file is going to include the header file from your Spotify.h header file, and it's going to be able to access some of the functionality that's in the C file. Some of the other functionality in the C file is hidden, so it doesn't have direct access to the structs. There are helper functions that the C file uses internally, and the main file won't ever see those. So some of the stuff can be seen, but other stuff can't. The trick then means that if we have this separation between all of the capabilities of the library and then what the library actually presents as the functions that you can call, means that anytime you want to make changes to the library itself can verify whether the changes you're asking for are correct or not. So because you never have access to the internal structs of the library, you can't accidentally do anything wrong to them. So you can't accidentally delete them, you can't accidentally move the pointer away so that it doesn't access them properly anymore. Actually, I think you can do one of those. You can screw with the pointers by accident, because if you lose a variable, then you've lost the variable itself. So if you created a library and then stopped using the variable for the library, then you kind of lost it yourself. So you could still create memory leaks on your own. But there will be a nice set of files that says, okay, this is how we create it, this is how we free it, this is how you add something to it, and you're not manually adding anything to it, that kind of thing. So what we get is a situation where anytime you want to make changes to this data structure, any changes you make are verified by the code that's in the C file. So your main file tries to ask the C file to do things. The C file says, I will do this only if your request is valid. So it's nice that way because any code you write in the main file is sort of protected from accidentally making mistakes. When we're using these multiple files together, we will need to link them together using includes. So if you want to use any of the functionality presented by the other piece of code, so it's kind of like the main is one piece of code and the two Spotify files are a pair that work together. In order to use anything that Spotify provides, you would need to include the header file. And if you include the header file, then you get to see all of the functions that it provides, as well as the actual type that is the object that can be worked on with those files. And that's actually the thing that is the abstract data type. So in your case, it's the library. But the cool thing about Spotify is it actually shows us a library, a playlist, and a track. It actually has 3 abstract data types in one file. They're all kind of working together, so it's sort of okay for them to be in one file. But if we were going to expand this implementation and make it really big and stuff, we would probably separate them. So we would have a library.h and a library.c, a playlist.h, a playlist.c, and a track.h and a track.c, and each of them would have their own capabilities, so that if a library was going to manipulate a track, it wouldn't be able to accidentally change or break the internals of the track. It would just call functions that would change the track. And so we'd have that abstraction separated over multiple pieces. We didn't do that for the assignment because we didn't want to throw, 20 files at you. Because of the last assignment, we had 1 file, and this one's already splitting up to about, I think, 6 or 7 files and stuff. So there's already stuff like capture that we wrote for you just for your testing. And then in the project, there's also multiple ADTs going on in there. So there's a lot of work happening as well. The other thing to remember is the implementation files, the C files, are never included. So we only include H files, but conversely, we compile all the C files, but we never compile any header files. And you can kind of see why, because the header files don't really have any code in them. So they don't go into compilation. Compilation is going to translate everything we've written into running code. So the H files are already kind of there, because the H files will be included in the C files, so we only need to compile the C files. Girachan's asking, what is if ndef? That's something to do with including, where it says, if this thing hasn't been defined before, then define it now. So if you're including the same H file multiple times in a project, this is like side details. We don't really go into this yet in 1511. But it means that if you've included something previously, you won't include the code again, because it says one of the other C files also included this same thing. So just have 1 copy of it. We don't need 2 copies of the same thing. So that's what the if not defined thing is. So Rosie's saying, sorry to interrupt, being a weird error in DCC, claims that didn't initialize a pointer before using it, but in the except I did initialize the pointer. Hard to say, Rosie. I think that one's something you're going to have to get someone to look at personally. So there's going to be something that you're doing with that pointer that might be trying to access it before it's given a value. And it might be somewhere else in your code that you haven't noticed yet. So you might be calling a function on a pointer without having given it a value yet. You could always try to initialize it as null before you do anything. And that way you might see then, because you'll get an error when you do use it, if you're trying to use it, and you'll get like a accessing a pointer that's null. You'll get one of those kinds of errors, and it'll tell you exactly where that's happening. So that might be a way of finding that out. Okay, so when we're using multiple files, we know that the code's in the C file, and the header is like the recipe for the code. So the headers are included, the code files are compiled. a good example of this, and I've already started talking about this a bit, is your Spotify. So your second assignment has an ADT and an abstract data type. So we can see that, oops, I just accidentally unfull screened by pressing a random button on my mouse. So the way that we separate the two files, because Spotify.h only has defines, type defs, function declarations. Type defs I'm going to talk about again, because I mentioned them previously, but I want to go over that. And it's commented a lot, so you can kind of see that the H file is there very much more for human usage than the computer. I mean, it definitely has uses for the computer, but a lot of the time we consider the H file to nearly be the documentation for our entire piece of code. So sometimes when the H file is put together well enough, we don't actually have other web pages for our code or anything like that, or if we have those kinds of web pages you may have been looking up when you're looking up libraries, they would just be a copy of the comments in the H file. And you'll notice in our assignment specification kind of pushes that idea, because we don't have all the detail in the assignment specification. Instead, we've put more of it in the H file. So we're sort of shifting you towards the way that we might be doing this when we're doing this in person, because you know that everyone who's going to work on the projects can see the H files. They may not always have access to the documentation we've written. The H file always kind of has to be up to date because it has to be compiled. So it's kind of safe for us to put all the information in there. The C file contains the actual structs as well as all of the running code for all the functions. These two will always match up in a certain way, in that anything that is mentioned in the H file will be implemented in the C file. So we can't have functions that are just hanging and don't have any code that runs. So if the function has been presented to exist in the H file, we will have implemented it in the C file. And you'll kind of see that to a certain extent in Spotify, that we're expecting, well, not everyone, because not everyone's going to finish absolutely everything in the assignment, but we're expecting that we have laid out all the H file functions and you're going to go through one at a time and create the implementation for all of those. Looking in chat, I think people are just helping Rosie out with stuff, which is cool. So thinking about how some of the other files interact with the Spotify abstract data type is that the main will include the H file. Including the H file means that you can then get access to the functionality and it will use the functions in Spotify. Interesting thing is the test main.c along with the test Spotify.c and the test Spotify.h, this other setup. There's two possible programs in the second assignment. So one is running it via the main. So you compile the main and your Spotify.c. You will get the interactive version of the program where you can actually type in letters, build up the playlist and stuff. But the test main.c has its own main function. So you will either compile with the test main.c or the main.c. And if you do compile with the test main.c, you'll also be using the same abstract data type. So the abstract data types are the same. We're going to use them both. But depending on when you depending on which one of these you compile with, it's going to run a different program. So if you compile with the main, you run the interactive program, but if you compile with the test, you run the automated testing thing. And this is really cool because this is showing you the fact that if we have an abstract data type, so if we have this multi-file project in this set of files, it's like we've made our own library. And if we've made our own library, we can use it in multiple programs, because we've seen definitely that we can use libraries in multiple programs, right? Because we've got the standard input-output library. And over this course, there's 500 people, and each of you has done 50 lab exercises. We're talking, what is that? 25,000 separate programs, all using the same standard input-output library, but creating a different program. So there's something really cool about that the standard input-output code has been reused so many times for so many things. And if we look at all of humanity and everyone who's written C before, standard input-output has been in so many programs. So what we're getting at is this idea that we're never going to reinvent the wheel. That's the saying, right? We don't want to redo work that has been done before. I know, like, this is like a weird thing to say, because as students you're redoing a lot of work that people have done before, but eventually you get to the point where you want to do something and you can't just Google it and someone has done it before. You want to create something that's completely new. But when you do that, you want to make use of all of these bits that have been made before, and you don't want to remake things. So that's one of the things that abstract data types give us. They give us the ability to say, this code was written, it can now be reused multiple times. And it's a much nicer way of reusing things if you just include the H file, compile the C file with it, than having, say, finished, say, assignment 1 and say, oh, I want to use some of these 2D array structures. I will have to copy paste sections out of that code and copy paste those sections into my code and hope they kind of link up. When we have built things in a format that is made to link up, it's much easier than grabbing bits and pieces and hoping you've picked up everything that you needed. So this is what we're getting towards, is the ability for us to kind of carry around a tool set with us of previously written code that we have, knowing that the only interface we need to think about to that code is a couple of functions in the H file. We never have to delve into the C file to be really sure about what's going on. Gira-chan, not everyone will finish everything. Everyone, challenge accepted. Please don't hurt yourselves over the assignment. It is fun to try to complete everything, but I know that this year has been going for at least a decade now. The longest year hopefully this will be the longest year of all of our lives, and we've had to be very separated. We've had to be alone a lot in what we're doing and stuff, and so it's been a rough year. So please don't push yourself to the point of exhaustion or anything like that just over an assignment. It's not worth all of the marks in the course. The course is not worth all of the marks in your degree either, so it's not going to be like, well, hopefully not going to be the end of the world or anything if this one assignment doesn't complete entirely for you. What are we talking about here? Stefan's saying, every time I use malloc to create a struct pointer, e.g. the pointer equals playlist, then malloc it, the pointer becomes a brand new struct. Yes. Anytime you use malloc, you're creating a new struct. If you want a pointer to point at something, then aim it at something, but don't memory allocate, because if you memory allocate, you're going to replace the pointer with something else. I think people are talking in chat about this already. Right, okay. Chat's happening there. I won't answer all the questions in chat because you're talking to each other a little bit there, which is good. Okay, so abstract data types. I've said the phrase a couple of times already. So now we're going to think about this from a conceptual sense. An abstract type... Sorry. I'm going to slow down. An abstract data type is a type that we can make for our own purposes. So what we can do is we can give a type a name. So for example, library, or playlist, or track, things from Spotify that we've got. We can say there are certain ways that you can then interact with this type that we've created. So declaring the type is the type def. Then I think I've got a slide about type def coming up in a second. Then the way that you can interact with that type is the functions provided in the H file. So what we do is we don't expose the internals, we just say these are the ways that you can access it, and as I said before, this stops people from accessing the data incorrectly. The way this works then is if someone's using our code, they can only see the H file. They can't see the C file, so they don't know what's going on underneath. But they can see how they're going to use things, and so the nice separation there is you don't need to know everything that's happening to be able to use the code. So there's a lot of code in the C file that you won't have to see, but you only look at the small amounts of code in the H file, and then you can use the data type entirely. Questions here about marking. Anson's asking, will the average mark of assignment 1 be revealed? No. So we're not necessarily going to release averages and stats or anything like that. People often ask for rankings as well. I don't release those either. I don't want this to be a measure of whether you're better than other people or not. I think the way that you measure a course is whether you think you've done well in the course or whether you've learnt something valuable from the course, and that's going to be different from your marks or your marks relative to other people. William's asking, does anyone know what's going on with lab marks? I think that Tom is marking all of the labs and things, but maybe not everything has been released. So I think maybe the lab marking is trailing a couple of weeks, a week or two behind the final submission dates for the labs. Hopefully that's still happening. I haven't actually looked, because from my end of the course, I don't actually look at the lab results or anything like that. Because I'm not really going to go through every single student and look at your lab results or anything. Whoa, Trent, we're 5 weeks behind? Okay, I'll have a chat with Tom and have a look at that. So we're 4 or 5 weeks behind. Okay, that's a little bit too far behind. So I'll go have a look, because I think there's a lot of back-end stuff that's running in the course that maybe is not running correctly at the moment, and we'll go have a look at that. So hopefully what we'll get is, in the next couple of days, we'll get ourselves back up to date and only be about 2 weeks behind, which is where we should be. But I'll go have a look. Okay, so back to what we're doing now is okay. So the abstract data type is going to allow us to present certain functionality, but then whoever uses our code doesn't have to know about how that thing was implemented or how it was made, but they can just know how to use it. So the type def is something that helps us do this. So when we are creating this abstract data type, we're going to give it a name. And one of the ways we do this is this type definition. So type def means a definition of a type. And so what we do is we take the original type that it was and we give it a new name. And giving it this new name means that from then on you can kind of use either name for things, but the intention is, if you're looking at something from the outside and you don't know what the internals are, you'll just use this single word name for it. So you use this abstract concept of a library, and then in the C file inside, the actual implementation will know that anytime we use the capital L library, we just meant a pointer to a library structure. And so underneath we will use the library structure, but from the outside you only think of the idea of a library. So the abstract data type is nearly like working with an idea rather than the nuts and bolts of what's going on. So after we've seen this type def, we can actually use either of these things to mean the other. So usually when we're including this thing, this is the first and last time we will see that there's a structure pointer somewhere in it. So we know that there's a pointer to a struct, and we'll never know what the struct is. So all we know is that that's a pointer, but we're going to replace that with the idea of something. And from then on, every time we use it, we're going to use the capital L. Yeah, so what this does is it hides the fact that there's a struct. I mean, like, you kind of know that there's a struct, but behind it, it just says what we're actually going to be using is this capital L that just says use this type, and we'll talk about what it actually means. So what are we talking about in chat? Tom's asking here, are the lab marks not just how you did in the auto test? They're not exactly. So they're going to be separate tests, but very similar. Just so that no one does anything really silly and submits something that says, if test input is these numbers, test output is these numbers. Like, you could just do if-else statements all the way through your code saying, if test input was this, output is this. If test input is this, output is that. And then you would get all the marks for the auto tests. So all the auto tests would pass, but you'll get no marks because you haven't implemented the actual thing that's happening. So that's the extreme case, which is why the auto marks are different for the auto tests. But you may have things that are more subtly doing that rather than directly doing that. So that's why we can't necessarily say that we'll give you marks just on the auto tests. We'll mark you on other things as well. Yeah. As you say, Thomas, there, the separate tests make sure you haven't cheated the spec by using advanced functions. You're saying, oh no, I'm going to fail all my labs, because all I did was, if the input is this, the output should be this. Okay. So, the type def is put in the header file. So, this means that everything that uses our abstract data type will see the type def, which means everything that uses our abstract data type will be able to see the capital L library. The other stuff that happens is like the underlying details, exactly what's in the struct, how it's used and things, go in the C file. So again, I've said this in nearly every slide I've talked about these. There's stuff that we can see. The stuff that we can see in the H file is the stuff we're going to use. The stuff that is in the C file, I should not have used the word C, but the stuff that's in the C file, the implementation file, is the stuff that actually provides the working behind the H file. So here's an example. I will move my face out of the way for this slide. We're going to talk about this thing called a stack. And I want to talk about the idea that when we're building an abstract data type, we talk about its name, for example, and the rules on how it is used. But other than that, we don't talk about anything like, we don't get down to programming detail on these things until we say, okay, the idea is complete, now how are we going to flesh it out? So, for example, a stack is something that I call a last in, first out structure. This is actually a concept that you're going to see with other data structures as well. So last in, first out means that we can put things into a stack, but if we take anything off a stack, we're immediately going to get the most recent thing that we put in. So the last thing that went in is the first thing that gets removed. So I like to think of it like a deck of cards. So if I have cards and I put them on the table and I'm making a stack of cards, the only cards I have access to are the ones on top. If I want to go through the cards that are beneath, I have to take the ones off the top first. So this structure gives us a set of rules for how we're going to put our information together. But notice that in these rules, I have not said the words linked list. I have not said the words array. I've not said the word struct or anything like that. There is nothing of that there. It's an abstract idea. And so the idea of how it's going to be implemented is just not happening yet. We haven't gone into that. Instead, what we're saying is we're going to use this idea to say that the most recent thing is the thing that gets used first. And that's it. Cool thing about this, I'll move my face out of the way again, is this is actually how functions work. So when I say I'm introducing a new thing called a stack, it's not actually that new. We've been using this for a significant portion of the course and just sneakily not talking about it. So this is actually called the function call stack. So occasionally you will see references to something called a call stack, which is all the functions that have been called in our program at any particular point that the program is running. So this stack is actually sitting in our memory. So we were talking about how all of our functions get a piece of memory. All of these pieces of memory are stored in the idea of a data structure. So any function that is running is on the call stack. So the first function that's always running is our main. So the main's the first thing that gets on the stack. Then, if our main calls a function, the function gets added to the stack. And note the way this works, because you can kind of see the way this works because we've been using functions. When we are in this function, the only code that can run is this function. None of the lines of code in the main can run. So, it works like that idea of the stack that we're talking about, that only the thing on top of the stack is accessible. Everything underneath has to wait until the thing on top has been removed before it can continue. So this is the same kind of thing. The main won't keep running until the function above it has finished running. The stuff is still there, so it's not exactly like that. So sometimes we can look at some of the variables in the main, but usually that's only if we've been given pointers, and the pointers are kind of breaking the rules for which things we can look at. If I call another function inside function 1, I will put a new function on the stack. And so what we're seeing is that we've preserved all the information of the other functions, but we're now running function 2. So when we're running function 2, nothing from function 1 runs, only the top of the stack is accessible, and nothing from the main runs. But then when function 2 returns, so when function 2 finishes, it says, okay, I'm done. We remove it from the stack. Removing it from the stack leaves on top of the stack the last thing that was on top of the stack, which is function 1. That will always be the function that called function 2, because it is the next thing in the stack, and so when that finishes, it will return to the main. So this stack structure, going up and down like that on the stack, controls which function gets to run at any particular point in time. So the coolest thing about this is we've been using this. So every time we call a function, we know we're in that function. That means it was added on top of the main. And then we can build up, we can call multiple functions on top of each other, and then we can return from them, or we can return from some of them and then call other functions. This thing can grow and shrink, but it'll always keep a perfect record of what functions have been running in the past in this program, and which functions need to finish before this program can finish. So this kind of structure is really nice. It just sort of holds everything together. I know saying I've got stack buffer overflows. What are those? Those are errors, but they're slightly different errors. A stack overflow is not necessarily the functions on the stack, but it's usually to do with the memory on the stack. So it's usually to do with things like variables that are put on the stack. So I think the classic stack overflow is if we have something like an array and we go outside of the bounds of the array, or we have a pointer to variables that exist, and then we move that pointer off those variables by accident, and then we start to try to go outside of the stack where the variables are. And so we say that is like overflow, like where we're going outside of the bounds of where we should be in the stack. So often that's things like we try to access a variable after it's disappeared. Things like that. So that's a slightly different stack. Yeah. Oh, as Gira-chan saying also, it's kind of like when the array goes out of bounds. Okay, so this is the stack structure. So it builds things up, and we can remove things, but the only thing we can ever remove from the stack is the most recent thing that's been put on the stack. So let's talk about this, all right? What makes this an abstract data type? Again, I said this a second ago. An array or a linked list is something that we can consider to be very specific, right? They don't just have specific rules. They have how they're laid out in memory, how they're accessed, how they're working in code structures. I have given you a definition of an idea here that in these two slides, I've said nothing about how this is implemented. I've said nothing about how it's laid out in memory. I've said nothing about the code that makes it work or anything like that. Yet you have an understanding now of how this thing works. Like a deck of cards, you can only take the top card off it. Or like these functions, the only function that can be run is the one that was called most recently and hasn't finished yet. So it's abstract because it's an idea of how things could work. It does have a structure, but it doesn't have any actual nuts and bolts code implementation that's making it work. So with there being no specific implementation, this thing still has a very specific set of rules for how it should work. And so we can start to think about, if we were going to build one of these, what would be in our H file? So we could think of a header file saying a stack could be used a certain way. So it's going to have abilities to add things to the stack, remove things from the stack. It's going to have a setup to start the stack working. It's probably going to have some kind of thing to free the memory that was used in the stack or to destroy the stack. It might have some other little tricks like how many elements are in the stack at the moment, or can we look at the top of the stack without removing it? Lots of little things like that. But the simplest thing is it has to make sure that these rules that we've come up with, the idea of the stack, are implemented. And the cool thing about that is the header, again, same point I've been saying, the header doesn't have to say anything about how it did it. So the C file, the implementation file, could use any other types of things to store the stack of objects, but we don't need to know because it's an abstract idea. So you get this thing with ADTs where there's the abstract idea side and then there's the actual implementation side. And we're going to look at a bit of that today. So I'm going to go on break early so that we can do more programming later. I'm going to talk about the idea of abstractness with lots of the different programming languages. We have the idea that we're solving problems in an abstract way. You will realize the more coding you do, you will realize that a whole lot of the programming that you're doing is in stuff like this. Is thinking about ideas and thinking about how you want to solve problems, and then only later are you then going to specifically translate these things into the particular language you're using at the time. So a lot of what I'm trying to teach you in this course is how to think about logically solving problems, and then also how to translate that into C. So I'm teaching a lot of stuff about translating into C. But the idea of a linked list is the idea of connecting information together with these connections, which aren't always pointers. In C, they happen to be pointers. In other programming languages, they can be just references to other things and stuff. So it's interesting that C looks at memory layout and says based on memory layout, or we can get addresses to other things. But other programming languages don't necessarily work directly in memory, so they will have references to other objects that are different from our pointers. So the idea that you come away with is that you can build a linked list having objects that can see each other. And then when you use other languages, you will use whatever implementation or whatever specifics of that language that will allow you to do those things. So C's a nice one because there's a lot of big languages. A lot of people are using C++, Java, C#, other things. They're all based on C. I mean, pretty self-evident for these two, C# and C++, that they're based on C, but they're not the only ones. Like, even Python is based on C to a certain extent. It is definitely a more distant evolution from C than something like Java. Like, you can kind of, if you use Java, you could nearly get away with a reference document for some of the kind of standard library things. Don't think they're always necessarily called standard libraries in Java. And your knowledge of C, and you can program in Java. You know, you can definitely program in C++ using your knowledge of C. It's awkward because C++ is able to do everything that C does. You can literally copy paste C code into C++ and it will run. But the subtleties is if you wanted to learn C++ well, you'd want to learn a new idea of programming. But what I'm trying to say really here is that there are fundamentals for programming in general, and these are the things that you're learning. If you can learn how you want to talk to computers, the language that you use to talk to the computers is just one of the many tools, but learning how to talk to computers is the fundamental thing that will allow you to communicate with a computer in many different languages. All right, so let's go on break now. It is 11:49 on my clock, so we'll go exactly 5 minutes. So 11:54, I will come back and we'll start working on the detailed look at a stack and the implementation. I have some files prepared for that as well that we're going to look at. All right, back in a moment. Hello, I'm back. Looks like there's a lot of lively chat going on here because I mentioned new languages and everyone's talking about other languages and where we can go with other courses and stuff like that. So Raman's asking there about. I answered a lot of other questions I think in chat, but Raman's asking about what language is used for creating games. The underlying language for most games is C++. But the language is used for actually making games is often C# or C++. It's interesting that a lot of games nowadays are not being programmed entirely from scratch. So they're usually being built in engines. So I would say that I don't know if it's the most common, but definitely one of the most highly used game engines is this thing called the Unreal Engine. You can make a fully functional game in the Unreal Engine with no code, so no text code. You can actually do it via visual coding with these blocks and lines that connect between them, which is the idea that each block is a function and the inputs and outputs go in and out of these things via these actual lines that you can drag around. You can actually draw a diagram of what your code should do, and it actually runs. And the cool thing behind that is that the code underlying that diagram structure in the Unreal Engine is all C++. So you get the benefits of having one of the most optimized high-speed languages working under a programming interface that someone who actually doesn't understand code but understands the theory of programming is able to do it. So that can be a really, really interesting thing to look into if you're going into games. The two that I would say everyone understands for making games is the Unity engine and the Unreal Engine, so you can look at either of those. They're both free as well. They have really, really good business models for those, for us, because they're free to use, but if you start making a certain amount of money with them, then you pay. So it's good for them as well, because it means that all the students are learning. Anyone who's making games is making them using those engines to begin with, so it's more likely they will continue using those engines when they start making money. So it's a good model for them. Most game engines underneath are written in C++, but I mean, a lot of game engines are proprietary, so like I don't really know. I don't even know what the source code is underneath a lot of them. So I've never seen the code for the Cry engine, but I assume it was in C++. Older engines, like the Quake engine, was in C. So there's lots of different things. I mean, I haven't looked this up recently, so I'm just trying to pick stuff out of the back of my brain, so hopefully I'm not entirely incorrect there. Raman's asking if I've worked on a game. I've worked on lots of little indie game projects and stuff, but I've not worked on any commercially released game. Okay, let's continue with what we're doing. We're going to put some code together today. We are going to build a stack abstract data type. So, when we're building the ADT from the outside perspective, we're thinking that our user is going to see the stack, not the array or linked list, and they're not going to know. So they're going to have ideas of what things they could do. We're going to start simple. I mean, like every lecture example, I'm not going to put stupendous amounts of data into the stack. So I'm not going to make a stack of running code where I need a really complicated struct with like lines of instructions and pointers to lines of instructions and execution capability or anything like that. For the moment, we're only thinking about the stack part of it. So we're just going to put integers on a stack, right? So the payload's not as important as the data structure for the moment. So we need to think about some of the things that we would need to do to make a stack work. So we need to be able to create the data structure, which means that any of the setup code we have happening, we want to be able to destroy the stack when we're finished using it, which means that, or even if it still has items in it, we need a way to clean it up. And we're going to add and remove from the stack, and these are known as pushing onto the stack and popping off the stack. These are terms that we use a lot in programming, is push and pop from a stack. And we might also want to look at counting how many other things there are in the stack. I just threw this in, we don't always need it, but I threw this in as a possibility for us to have another utility function that we might use. It also helps with stuff like popping, because if we're going to remove things from the stack, and we don't know how many items there are in the stack, we might try to remove from a stack with no items in it, which is a potentially dangerous thing to do, because the removal is probably going to give us an object, and if there are no objects to give, what's it going to do? You know, there's nothing that works in that case. So that's why we might count how many things there are in the stack. So these basic functions, these basic capabilities are the kinds of things that we're going to make into the H-file functions, and then we're going to fill them out. So here's an H-file, but better than looking at the code on the slides, let's go to... I'm going to log into my VLab where I've copied a couple of files last night when I was doing my final prep for today. We are in lecture 15. I think today I actually remembered what which number lecture we're in. Okay, so I've got a full implementation here with a stack.c. I'm going to just rename stack.c for the moment by moving it to stack alternate. So we may have a look at that one, because that's an implementation I did last term. I think that's a leftover implementation from the last term, and I think that this is one using arrays, but what we're going to do is do one using linked lists, and we're going to look at the difference between them. So if I open my main.c and my stack.h in gedit, we don't have to look too much at the main.c. This is actually an old one that I used ages ago. But you can see that I'm making a deck of cards by adding cards to the deck. And I use just random numbers here. So I'm just putting numbers on the deck, and then I'm taking them off the deck. So I'm using the push and the pop functions here. We won't be able to do anything with this yet until we've actually implemented these. So the important thing to look at is the H file, and you can see, look how old this H file is. This is the beauty of H files. If I've already decided the functionality of something, I really never need to modify this, because the only things that are going to change is like maybe how I implement these functions, or if I wanted to add functions to this, which I don't at the moment, because this is going to do most of what I need to do. So I've got functions to create and destroy stacks, so stack create and stack free. I call it stack free because we know that we're going to be freeing memory here, so it's a nice way to remind whoever's using this that that's what's going to happen underneath. I can add or remove items from the stack, so if I push an item to the stack, I have to say which stack I'm pushing it to and what the item's data is going to be. And if I pop something from the stack, I need to know which stack I'm taking from, and I'll get given back the data from the item. So this might be more complicated in an item that has more complicated data. And we also have the ability to check on the size of the stack by saying, if I give you this stack, can you tell me how big it is? We're not necessarily going to implement all of these today, but we'll do some of them, because I think the way that I'm putting this together is going to make it reasonably easy for us to do most of these functions. Izzy's asking if VLab will be available in the holidays. I'm thinking of finishing off challenge exercises and stuff like that. Yes. VLab runs for summer session courses and stuff like that as well, I think. I'm trying to think about what's running in summer session this year. But VLab will be running for most of the holidays. It won't be running for all of the holidays. There will be a little bit of time, because that's like, the only time that our system support people actually can get us to promise that we don't need it for our students. So at that time, they may do upgrades on it and stuff. So there may be a couple of days at a time where it's down. But for the majority of the holidays, because it goes for what does the holiday? It goes from mid-December to mid-February. So for the whole of that 2 months, for the majority of that time, VLab will be accessible and you can use it. Anu's saying that if we were to implement a stack using an array, one of the differences is that the array might be limited in size. That's a very astute observation, and it is true. So that will be one of the things that will happen if we were to implement the stack with the array. It does have one limitation that the linked list implementation of stack wouldn't have. Raman said he's behind you. Is there something in this code that I've gotten wrong? I'm not sure. I haven't looked at it. Oh, were you talking about the fact that this code won't run yet because it's not implemented? Miguel's saying, is it possible to make a stack using some reusable code that doesn't need to change when you use different data types? Yes, kind of. There are ways of doing that. I can't remember. So this is me branching out into the fact that I'm a C++ native and I translate a lot of what I do into C as I'm teaching you. But there is these things called templates that you can use. I don't know if they're in C or C++, but what they say is you can actually create a struct that says this thing contains a variable. And you don't actually have to say what variable it is. You can say that when someone uses this, they can choose what variable goes in there, and it's not necessarily going to be a fixed variable type on declaration of this thing. But when you start using it, you would choose what variable goes in, and then it can work with different variables. But I don't know if that's C or C++. So you could check it out. You can look it up, actually. You can look up templates in C and see whether they're actually used, because I've only used them in C++, but I can't remember either they're part of C++ that doesn't exist in C, or they're part of C++ that does. So you can look that up if you want to and see if that works. Oh, so Raman, there's a mistake in main somewhere. We'll figure that out. We'll figure that out later. I can't see it definitely, but we will. We'll figure that out as we start to use it. Okay, so I've got my recipe for the things I want to do. I have the thing that wants to be able to use that. And so it's interesting that we can write our main without knowing how these functions work underneath, but we expect it to work because we're calling the functions based on the comments here and what they said they would do. So we've got our header file here, and we're going to think about what our header provides to our main, but in brackets here are also being careful to say what our header does not provide. So the functions that we get out of this, we can push or pop an element from the stack. We are not given access to anything else. So once we've started putting things into our stack, we can't go through and look at what's underneath the top of the stack. So note that the only way we can get information out of the stack is by removing the top element from the stack. We can see the stack size, but that's not going to give us information on any of the data that's inside the stack. So I am being protected from accidentally going deeper into the stack and looking at things underneath, because that's not how it's supposed to work. We can only pop one element at a time, which is trying to make sure that every time we remove something from the stack, we are taking that information and using it. We are not able to loop through the stack, right? So if I said this thing is just an array, then we'd always be able to look at every element in it, which means we could potentially look at the elements we're not supposed to. Like, we could potentially break the rules of the stack if I just made it an array in my code, or just made it a linked list in my code. So what the stack is doing is it's saying, nope, there's a boundary here. You don't get to look at those things inside. You can just ask me for the top item if you want to. Oh, so Miguel's saying templates only exist in C++. I apologize. It was just something from my distant memory, so I thought I'd mention it. But everyone else, just block your ears, block your ears. It's it's not available in C. So the other option is to use pointers that don't have a type, so that you can access any type of variable. That is very messy, and I'd be very careful with that. Yeah. So I think what that means is if we're going to make a stack, we would just be using, for the moment, stacks of a particular type. Sorry, bit of a bug in the throat today. Okay, so let's look at the stack.c. The stack.c is something that we haven't created yet. So the headings in the header are each of these functions. we're going to fill these out with code in the C file. So we're kind of going to go through each of those functions and say, okay, we just need to make some code in there to make those work. Everyone who started the second assignment will know a little bit about this, because I'm following the same kind of development pattern here. I mean, I'm doing it in only 1 hour, like a much simpler example, but you will see this kind of thing in the assignment. So I now, if I'm going to make my stack.c, I need to start making some decisions. So if I'm in the C file, it means I'm doing the underlying stuff. I'm doing the underlying information. So I need to actually say, what will the actual data structure be underneath? So up until this point, all the abstract thing has said, nope, I don't think about specific data structures. But now that we're in implementation in the C file, we do need to start thinking about that. So the first thing I'm going to do is do this as a linked list. So I'm going to say a stack would work really well as a linked list, because as you can see, the stack changes length. The stack happily changes length. So a linked list seems to be a decent way to happily change length. Also, only the top of the stack is available for us to work with. So the fact that linked lists are organized via a head pointer, like a pointer that points at the top, well, not top, the first element, means I can make the first element the top of the list, and I only make changes to the first element. And so the linked list will actually work quite well for us doing a stack, because the stack says you'd never loop through, so I'll just never loop through. So I'll only use the top element. So I can already see how the linked list is going to be really easy for us. So starting off, get my face out of the way of the words, we will do some structures that are going to allow us to manage the stack. So the first one is, I'm going to call it stack internals, and that's going to be the all the internal workings of the stack. And you can see that I was already planning on doing that because of my type def. My type def here said there was a pointer to a stack internal structure, and the stack.h doesn't even know what that is, right? This is the first line of code here. It just says that somewhere else in this program, something else is going to fill out the rest of the information about what this struct pointer aims at. So it's interesting that I can actually create a pointer to something when we don't know what it is. We just say, we trust that somewhere else something's going to say that stack internals exist. But for the moment, we're going to say that if we use the capital S stack, something else in our code can use the capital S stack as if it was a pointer to the internals of a stack. So let's create that file, stack.c. So it'll open up in here, and I will say implementation file for stack demo. C stack.h for function headers and documentation. What are we? November 2020. Okay, so if I've got this C file, I'm going to want to include my stack.h first. Now remember, the difference between including a standard library that's part of C, where we don't know where the files are, we're asking the compiler to get those files, would be in these angle brackets. If I'm including something where I do know the files are, I'm in the same directory as those files, and I created those files, I use the quotes. If my stack.h was in another folder, I could say something like, I'm just assuming if I had it in another folder at the same level called stack library, I'd go up a folder, go to the stack library and the stack.h. So you might see this kind of thing. For the moment, we're keeping it in the same folder, so I'm just going to say stack.h here. So this means that stack.c knows everything that's in this file. So when I start implementing these functions, I know that they've been declared previously. So the first things I'm going to put together are my structs. So let's make sure I'm spelling this exactly the way that I had it here. Stack internals, So we're in camel case this time. For the moment, this is just going to create, just going to be a pointer to the head of the stack. And so I'm going to need I'm going to call it a stack node. And that's the head of the stack. Note, I can do this again if I want to. I can declare a pointer to something without knowing what it is. So long as later on, there's some information about what that thing is. Because I can have a pointer without knowing what it ends up being, because the pointer is just a 64-bit memory address integer, and it doesn't change it. So I can actually declare it without knowing what it is. However, if I'm going to use it, I'm actually going to need this stack node to exist. So the stack node is going to be our pretty bog standard linked list node. Like, there's nothing else that we're going to keep in here. So for the moment, the payload is just an integer, but if we wanted to change that, we would add some other stuff. So if I wanted a string, actually maybe it would be an array, I don't know, name or something like that. I would also declare that in here. For the moment, I'm not going to. I'm going to keep this simple. To make this a linked list, it needs a pointer to another stack node. So struct stack node next is my next point. So bog standard linked list struct, a umbrella struct that holds the pointer to the head of the linked list. At the moment, this is a little bit superfluous because it's like having a struct with only one variable inside it. It's kind of like we could have just had the variable. But even with only one variable, this thing is valuable. Because if I create this and this is null, the pointer here is null, I've still declared that a stack exists, but happens to be empty. If this thing was null, then nothing would exist. So it's nice to have this thing saying, I can make this thing, and it's ready to receive elements, but it doesn't have any yet. But I can also potentially put more information in here. So if I wanted to, I could do something like stack size. And so I could track the stack size in the stack internals. Things like that. Or if I wanted to, depending on my implementation, I could have a pointer to the top of the stack. I'm probably not going to need a pointer to the top of the stack, because I'm pretty sure my head is actually going to be a pointer to the top of the stack. But there's little things like that we can put in there whenever we need. So I'm just giving you examples of things you might do for other ADTs. Okay, so this structure gives us our standard idea of our linked list, like so, and our governing object giving us access to the linked list. So you will see this diagram, obviously much nicer version of this diagram in the assignment, because the library is the governing object, and then the playlists are the linked list objects. And then we have track lists inside each of the playlist. But for example, today for the stack, we're just going with the top level setup here. So the way we had a library and playlists. That's for those of you who have started the second assignment. Okay, so we've got, sorry, going back to my slides, we've got our structs, which get going. Raman saying, literally drawing out parts of the assignment to see what you actually have to do makes it so much easier. Yeah, and you can see how, now that we get to the second assignment, the first assignment was a lot of just learning how to write C. The second assignment is learning how to program, which is a lot more about thinking your way around problems than it is about writing C. The first problem is thinking your way around your problems. The second problem is then translating your solution into the language, which is like a test of how well you know the language. So there's both things being tested there. Okay, so let's create a stack. If we're going to have a function to create something, then usually that means we need to memory allocate it, because if we don't memory allocate it, it will disappear. So I'm thinking that this being a linked list, we're going to memory allocate each node. We're going to memory allocate the umbrella structure, which is the stack internal structure. So for the moment, where our stack create is going to create an empty stack, which is going to allocate the memory for the stack internals, and then it's going to set the head inside the stack internals to be null to say there's no elements in the head yet, and then we can give back a pointer to the stack we created. So we can nearly think, it's not exactly like that, but we could nearly think of this being the top of the file, this being the bottom of the file, and the main being sandwiched in between them. So if we're going to put this all in one file, that's what it would be like. So this is going to implement these. So let's create a stack. Create an empty stack. And so to create, we are going to do some memory allocation. We are going to allocate a stack internals. So we need to tell malloc how big of an object we are creating, which is a struct stack internals. Malloc is going to give me back a pointer to this stack internal, so I need to store that in a pointer. The cool thing is I can use this type def now, so I can either say I want a struct stack internals pointer, or I can say I already know that a struct stack internals pointer is a capital S stack. So I could just say this stack. I called it new stack in the lecture slides, and I'm happy with that because we're just creating it. Is the memory allocation of a stack internals. So this stack can be thought of as the same thing. Actually, I'll put the comment above. So I can use stack wherever I was thinking of using struct stack internals pointer, because the type def allows me to go either way. And we know that already because I'm going to be returning a stack, so I might as well use the same type that I'm returning, knowing that if I want to, I can use it as if it's a pointer, which I will do immediately, where I say new stack, and I'm going to treat it as if it's a pointer, and say the head inside new stack, which is the variable that's inside the structure that we're pointing at with stack, is going to be null because I don't have anything in my stack yet. And there's nothing else that we need to do here. So I'm just going to give back, just give myself some space. I'm coding in the middle of the screen. I'm going to give back new stack. So now I can create a stack. That's nice. So if we're creating a stack, then we're saying we've now got our abstract data type and we can start adding things to it if we want to. Raymond's saying we can do size of stack. Just be careful with that. So let's look at our type def. Our type def says capital S stack is a struct stack internals pointer. So can you think about how big, what size we're going to get if I do size of stack? So if I did something like, I'm just going to put some other code in here. Int size is equal to size of stack. I'm not sure whether that needs a space or not. What would we get here? Yeah, so what we get here is the size of a struct stack internals pointer. So no matter what we put into this stack internals, this would give us the size of a pointer, which is 64 bits in a 64-bit system. It won't give us the size of this structure. I mean, it will at the moment because it actually contains a pointer, which is really, really dangerous. So we want the size of struct stack internals, not the size of a struct stack internals pointer. And the stack at the moment is a struct stack internals pointer, but we want the size of this actual struct. So we just got to be a little careful there that we don't use the capital S stack in there. So that's to your question, Raymond. Raymond was asking if we can do size of capital S stack. We can't actually, because that thing's a pointer. We're looking for the size of the actual object. Okay, so we can create a stack. So Raman's asking, kind of confused, aren't we only allowed to access the first part of the stack, but it's a linked list at the moment, which means we can go through all the nodes? Yes. So the stack here says the functions that can be used on the outside, the stack push and the stack pop. So let's think about the car analogy that I was talking about before. When we're in the main.c, we're sitting in the driver's seat of the car, which means the only things we can do is turn the wheel and press the pedals. We can think of turning the wheel and pressing the pedals as being these functions. When we're in the C file, we are building the car's engine. So when we're building the car's engine, we know that when the person presses the accelerator, they expect the car to start going forward. But we're going to make sure that the car can't go forward in an explosive way or anything like that. So we have access to the engine here in the C file. But in the C file where we have access to the engine, we need to protect the engine from being used incorrectly. So when someone tries to do push and pop, we make sure that only the right things can happen. So we say that you can only get the top element of the stack. But in here is where we actually guarantee that only the top element of the stack is visible from the outside. So it's kind of like when we're in the C file, we're inside the engine, and we're in the main file, we're using the car. So we don't look inside the engine while we're using the car, but while we're building the engine, we're looking inside it and making it work. Hopefully that gives you some more information about the separation between the things we're working on here, Raman. Okay, so we've created a stack. The next thing we're going to do is we're going to push items onto the stack. So this is the kind of structure that I'm using here. I'm going to say that here is my old stack, where the newest element and older element, the oldest element, are already in this linked list. I mean, it could be empty as well. And what I'm saying, the new element gets added on at the head of the list. And all the other elements, the new element comes in. None of them will change their order, because the stack keeps its order. But I'm going to add a new element at the top of the list. And if I was to remove an element, the only thing I could remove is whatever the head was pointing at. So some code here for pushing onto a stack. So what we're going to do is we're going to get our functionality first. I'm not even going, at the moment, I'm not going in order of these, because the stack free is just freeing the memory in a linked list. And we've actually already written code for that last week. So I probably won't even do that today. I'll let you add that in if you want. But I'm going to do these things that we haven't done before. So to push onto the stack, to add an item to the stack, I might actually put some information here as well. That way, if someone reads these comments, they can say, okay, when they were making this, they had an idea that the head was the top of the stack. So if we're going to add an item to the top of the stack, and we've been given the data for the item, the first thing we're going to want to do is create that item. So I'm going to say stack node. Yes, stack node. Stack node pointer. So I'm going to have to memory allocate for the new item. So stack node pointer, let's call it new node, is equal to memory allocation. So I'm doing the same kind of thing, memory allocating a stack node somewhere in my memory. So it's like I said, make a new one, turns up here, and this is my newly allocated memory, and I'm given a pointer to that, and I'm storing it in stack node. I'm going to call it SN for short. and this is the head pointer here pointing at the stack. So this thing is the stack. That should have been a capital S. Yeah. Okay, so I'll continue doing that with the diagram here as I write this code. So first thing I'm going to do is I'm going to create a node, and then I'm going to add that node to the head of the stack. So I've been given a stack, which is S, and an item to go in. So what I would probably want to do is get my new node and say it stores data. So my new node's data is equal to the item. So now I've set this thing up. The new node's next is going to have to be something as well. So if I'm going to add this new node as the new first element of the stack, if it's going to be the first element of the stack, then its next pointer should aim at whatever the head of the stack used to be. Here. So I copy the head pointer from the stack and I say that's what my next pointer is going to aim at. So my next pointer will be my stack's head. And this is going to work whether or not the stack exists. Because if the stack is null, then my next pointer is null. That's fine. That means I become the only element in the list. If it was other list elements like this, then I'm joining myself up correctly to the rest of the list elements, so I'm in the new head of the list. So this creates the node. Create a new stack node and attach it to the current stack. Then aim the stack's head at this new node, because no matter what happens, this new node is going to be the new head of the stack. So the head of the stack is actually the top of the stack. So I say stacks, because I was given the stack, and I say the stack's head is now pointed at the new node. Oops, new node. So what I'm doing then is I'm saying this head pointer here, this thing's no longer the top of the stack. This new thing is going to be the top of the stack. So I will say, please aim the head pointer at the new thing. And there I have created a new element, and I have made it the new head of the stack, and it's now on top of all these other elements in the stack. Oh, hey Tom, how's it going? Right, Tom can answer questions if you need about stuff as I'm doing it. Oh, Tom, there are questions about marking labs. People would like to get their lab marks. There was a discussion about it earlier. Okay, so now I can add an item to the stack. So I've created an item, I've put the value in from the integer that I was given, and then it goes on the head, and the head then moves to this new node that's created. So now I'm getting this kind of structure here where I'm adding an element onto the stack and it becomes the top of the stack. Ah, that's good. Oh, Trent said, I think a whole bunch of stuff just got marked. Tom was already doing it while we were talking about it in the lecture. Okay, sorry, my face was covering up the head. The head was covering up the head of the stack. So that diagram there now should make more sense. So we're adding that element to the stack, this element to the stack here, now that I've moved my face out of the way. Having said that, I'm about to go on to other slides. So here's my code. I think it's the same code that I was writing there. I just changed where the comment was here in the slide. So the other thing that we're going to be doing sometimes is removing the top of the stack. So remember that we're taking the head pointer to be aimed at the top of the stack, which means this node here, the newest element, the most recent element in the list, whether we've just added it or not, or it's been there for a while, it doesn't matter. As long as it's the most recent element of the stack, it's the thing that's going to get removed first. So it's going to be the head of the stack. So we've got some code here for popping from the stack, but let's go in and actually write it instead. So stack pop. So we're going to remove the top item from the stack and then return its data. Tom, that's pretty funny. He was going to do the marking earlier this morning, but I killed the server we do our marking on. Fun times. I'm interested to hear the backstory behind that. Okay, so in order to remove the top item from the stack, what we need to do is first we need to find the top item in the stack, and then we need to give it back. So we know that the top item in the stack is going to be S head. Oops. So S is the stack we're looking at, and its head is the top item in the list. Now, I can't just give back that. So I could be very tempted to just say return the stack's head's data. But this is fraught with potential issues here. One thing is, if I just return this, I haven't removed the top of the stack, so I need to actually take that element off the top of the stack. The other thing is this thing might not even exist. So I might need to check whether this thing exists first. So let's not just go for the simplest possible solution we could have here. So check whether the head exists. So if statement, if the head doesn't exist, then we have a problem, right? There are no elements in this stack. So we're actually in a very, very serious quandary here, because stack pop is going to return an integer. If stack pop is going to return an integer, then what I'm saying is that all integers are valid for this stack, and I don't have the luxury of something like getchar that says that all valid elements of getchar are positive integers, and so I could return something like -1 or an EOF define or something like that to say that this thing is not a valid member of the stack. But I've said that this stack says it can store any integer, which means there's nothing that I can return to tell people that this isn't working. Well, there's nothing that I can return that might not be a valid element to store in the stack. So if I've popped from a stack that there are no elements, I'm actually kind of out of things that I can do. So I need to say there's a problem here. I'll say attempted to remove, I'll say pop element from an empty stack. And I might have to throw the whole program at this point. I don't know how things are going to work, but I think I'm going to have to throw the whole program. So I'm going to return 1 at this point, because if I give back any information, that's me giving the implication that this pop worked. But I can't give the implication that this pop worked because something went wrong. So I'm going to say, for the moment, we're just going to cash out here. We're just going to let this go. If you wanted to work on this and put more time and effort into it, you might have a more nuanced response here. For example, what I might do with stack pop is I might do something like check stack size first and never call stack pop unless stack size was greater than or equal to 1. So there's other ways around this potentially, but I do think I need this at this point because there's possibility of calling pop on an empty list, and I don't have a good way around it. I'm going to treat the rest of this code as an else statement without even writing the else statement, because I know that if this is true, this whole thing ends. So I'm just going to continue. And I could say, if we reach this point, there is at least 1 element in the stack. Okay, so if there is an element in the stack, I can think about giving back its information. So what I'm going to do is first grab the information, because if I'm going to remove something from a linked list, if I'm going to remove something, it's going to get destroyed. So I need to save its data before I destroy it, so before I free its memory. So int... pop data, because it's going to be the data that gets popped, is equal to the top of the list, which is the head, and its data. Then I'm going to do a removal of the head of the list. So remember, the way that we were removing from a list is we're skipping a pointer over something, and then we were saving a pointer to the thing that was being removed and using that pointer to free it. So I will... it's a stack node pointer. Removal node is the same as the head, sorry, the stack's head. So I take the stack's head and I say, this is the thing we're about to remove. We've already taken the data out of it, so I know that we can remove it. But then what we're going to do is say skip over it. So let's take this example here. So this is the state we're in now. So the head pointer is pointed at this first element of the list. So the first thing we did was we took the data out of it. So let's just say this had the number 5 in it. So I'm going to say I'm eventually going to return 5. So let's say I saved that elsewhere. I then make a rem node pointer pointing at the stack's head. So let's get a different color. Rem node pointer is pointed at the stack's head because the stack's head is currently pointed at this pointer. So that's my remove node pointer. Then I'm going to say the stack's head now has to be pointed at the rest of the list because I need to have the rest of the list still a valid linked list before I remove this node. So I'm going to say that my head pointer is now aimed at the node that I'm removing. It's next. So what I'm doing there is I'm taking the head pointer and I'm saying you're no longer pointed at this, you're pointed at its next, which is this element here. And there, that's enough. We say we're now pointed here. And so we still have access to this node because we have the remove node pointer. I'm actually going to get rid of that because that was a temporary variable we used when we were creating this node. So that's actually been gone for ages. So we have a pointer to the thing we're going to remove, and our stack is now just these 3 elements because we're removing this, but we've saved the 5 to return. So now we can free what the rem node is pointed at, which will take this memory and give it back to our computer. So I can say free rem node, and I think that's everything we have to do, because now if I leave this in this state, my stack is still well formed. This is gone. Oh, I still need to return the value that I've taken. So pop data is what I'm returning. Right, and that will give the integer back like that. What are we talking about? Oh, just talking about marking stuff. Okay, so this should have our pushing and popping happening. But we probably want to test this. Actually, should have tested this a little bit before this point. One thing that I have used out of instinct is printf, and I haven't included standard input output. Actually, I might do this first. A lot of us will separate the types of includes so that we know which of them are our own files and which of them are standard library things. So I've included the standard input output because I'm doing a printf in here. Okay, I think that I really do need to do some testing here, so I need to do some pushing and popping. And I do have this that's going to create, push 3 times, and pop 3 times off this deck of cards that I've created here. Someone was saying to look behind me at this point, so maybe there's something here that's going to cause a problem, but I'm going to try compiling this whole thing together and running it and seeing what happens. So let's clear this. And so compile. Remember, when we're compiling, we want to compile the C files, and we trust that the H files that we're going to use are there because of includes. So I've got my main.c and my stack.c. My output is going to be called stack demo. Oops. What have we done? Oh! Implicitly declaring library function malloc with type void blah 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 stack new stack equals malloc something. So I'm calling a library function to memory allocate without actually grabbing the library itself. So getting the fundamentals right here. I think it's quite funny that I even talked about needing to include standard input output for things, and I just went through and I'm using malloc here without even grabbing the library that provides us with memory allocation. So let's grab the standard library so that we can do memory allocation. And we'll compile that again. Okay, compiling this time. Miguel, no, DCC does not include standard library by default, which is interesting because the standard library is like the thing that nearly all C programs need. But we do explicitly have to say every library that we're going to use. So the DCC knows that it exists. It has access to it and things, but it will only attach it to our program if we ask for it. I mean, like, you can see a reasonable example of the whole first 5 weeks of the course. We never used standardlib.h, although I think it may be included in the C file that we give you for the first assignment. I'm not sure. Because I remember sometimes when we write those C files, because a lot of us, when we write C files, we write this first, and then we just go on to write everything else, because we're just like, we're nearly always going to use both of these. And so they end up in a lot of files, even sometimes when we don't use them. Okay, so let's look at stack demo. Okay, so we put 42 on top of the stack, then 37, then 13. So 42, 37, 13. And then we popped 13 is the first thing that comes off the top of the deck, then 37 comes off the top, then 42 afterwards. So what we have there is a stack implementation that is working using a linked list to add and remove elements. I haven't completed this implementation because I haven't written stack free. I'm not going to write that today because I don't want to write the same code as I wrote in the last lecture. So you can always go back and say, how do I remove a linked list? So I will need to remove all of the nodes in the linked list that I get access to from here. And then after that, I will need to remove this structure that was allocated as well. So you could nearly, if you want to, is just compile this with a leak check and go, okay, leak check's kind of going to tell me where the memory allocations were, but it's sort of better for you to say, if I want to free a stack, let me look at all of the structures that make up the stack and make sure that I clean all of them up. It's probably better to know in advance than to only do things via leak check. It's like programming with correct theory versus just programming to the auto tests. So we could do our stack free like that. Our stack size, I gave you a clue for something that we could do with stack size, is we could have an integer here called stack size, and then we could say that when we create a stack, actually I'm kind of going to implement it here anyway. I could say new stack size starts off at 0. Let me write correct code now that I'm actually doing it. And then every time I add something to the stack, I'm going to say size goes up. And every time I remove something from the stack, I'm going to say size minus minus. And this means that my my function here gets really, really funny, my stack size function. Returns the current size of the stack. That's it. My function is a single line that says that I was tracking the size the whole time here, and all I need to do is give you that integer if you ask for it. But every time I remove something, size goes down by 1. Every time I add something, size goes up by 1. When I create an empty stack, it starts at 0. So there you go. There's a freebie. I wasn't necessarily going to implement that today, but I'll throw that in. Okay, so we've got code for pushing, code for popping, and there's other things that we haven't implemented that we actually have checked the number of elements. Sorry, not implements. We've implemented the number of elements. Say that 3 times fast. And I said here, you could store an int in the stack. The other way we could have done that function if we wanted to is instead of storing that integer, we could have looped through the list every time that's asked, and we count the number of times we loop through, and we would also have been able to give back the size of the stack. So let's think about different implementations. Get my face out of the way of the words. Stack doesn't have to be a linked list. So we could implement the functions in stack.h using a different data structure. So we could use an array. So we could have an array with a very large maximum size where we keep track of where the top is using an index of the array. So here's an example of how I could do this. I could say, here is my, whoops, I was pointing at the wrong screen. Here is my stack that has some integers in it, and top is 5. So top is the index of the gap here just after the elements I have. Now you'll see this is actually looking a little bit similar to how we would always have a marker point at the end of a string, so we can have this changing length of an array. But the top being this number means every time I add something, I can add it in to that number. Every time I pop something off, I move the top down 1, and then I pop this off. So I've got some code here for it. I've even got, if I open it, stackalternate.c. Stackalternate.c is a stack where I have a max stack size, so someone was talking about that, cluing in on the max stack size. If it's going to be made with an array, then you are going to have this functional limitation of how much memory for the array are you going to use at the very beginning, and that's as big as it's going to be. So if I tried to stack up more than 1024 items, I'd be in a bit of trouble. So I have an array that's that size, and I have an integer pointing at the top of the array. So when I create it, I just allocate memory for it and say where the top is. The top starts at 0, which means it's empty. The nice thing about this is that top index actually tells me how many elements are currently in the list, which means that, oh, I haven't implemented in here, but I could implement the size function simply by returning top. So when I want to push an element onto the stack, I can say, just be careful if we've used up memory. So we have that same kind of thing. Oh, I used exit 1 instead of return 1. Exit's actually a function that you can use. I think it's from standard library that will end the program in the same way that return 1 would have ended the program. Oh, wait. What am I saying? Return 1 wasn't going to end the program. Return 1 was just going to end this function. So I should actually use, I'm glad I looked at the other one. I should use the correct thing to say, end the entire program using this exit 1. So if I had attempted to pop the top element of the stack, I would have just returned 1 from this function. Whereas what I wanted to do was say the whole program should just bail at this point. Okay, so pushing at the top of the stack, I'll show you the diagrams for it because the diagrams are better than the code. So pushing the top pop, if I want to add something to the top of the stack, my top is 5 here, saying I've got 5 elements, this is this index. I will change the value stored in top to something else, whatever has been added to it, and then I'll move the top up 1. So the top's always going to count how many things are in it, and it's going to be the index of the gap afterwards. So this is just the idea of how I would implement this if I was going to do it as an array. Push does a similar thing where it says the top is here. What we would do is we'd move the top down 1. So we'd do -1 of the top, and we'd read the element there. Note that I colored this orange here, but the 8 is still there. The 8's actually still in that element. but now we consider that element to not be part of the stack because the top is aimed at it, and so the rest of these things are the stack. And if I was going to add something to the stack, it would overwrite the 8 that was sitting in there, and I can never read that 8 again. So there's a little bit of us working with the array and putting data in it, but trusting this top index to tell us where we are in the array. So I'm not going to implement it because we don't have time, but I wanted to show you that the stack can be done the way we did it using a linked list where we push and pop from the head of the linked list. And it kind of makes sense, right? Because a stack is only ever looking at one end of its list, and so having the pointer to the head of the list makes it really easy. But if we wanted to, we could do it with an array. So we could do it with this kind of idea that the top is an index marker that moves up and down the array. However, you can run out of space in the array, which is why I chose to implement the linked list, because I think that the linked list is a more intuitive way to make a stack than the array is. So the important thing we're getting to here is that the implementations are hidden from the main. So the main doesn't know what implementations we're using in the C file, and it doesn't have to know because it knows the header. And the implementations, when they're made, they don't make any changes to the header, which means if I compile my code there, if I was to finish making all the functions first so that it was complete, if I compiled my code with the linked list version, you could use it and you'd go, I'm using a stack, and it's fine, it functions like a stack. And if I implement it with my array, so I've got my 2 different files there, you could also use it and you wouldn't tell the difference. You'd have to be really, really trying to break it to be able to tell the difference. You'd have to put in so many elements that you reach that memory limit that I had there for the array. And that's the only way you'd be able to tell the difference between the two. Otherwise, from the outside, they'd look the same. So this is like the idea of, like, if we're sitting in the driver's seat of this car that I was talking about, and all I see are my H files, my H file functions. So H file functions are move the steering wheel, press the pedals. I don't know what the engine is. So is it a 4-cylinder engine? Is it a 6-cylinder engine? Is it a rotary engine versus a piston engine or whatever, you know? Or is it an electric motor versus a petrol motor? What I do with the steering wheel and the pedals doesn't change, and I still get the same result out of it. But underneath the implementation, someone else has made decisions about how this thing should work. So that's the nice thing about our abstract data types. We can do this kind of hidden implementation stuff. And I want to say that stacks are not the only abstract data type. We should know this because we've seen Spotify. Spotify has multiple different abstract data types, and they're storing information for music tracks or playlists and stuff. But there's another one that I wanted to talk about that we haven't covered. But you could actually, if you wanted to, you could take the code that we've made for a stack and you can make a queue out of this. So the stack had these rules of last in, first out, which means the most recent thing I put in is the thing that then gets removed. A queue is a slightly different thing where it is first in, first out. And a queue is pretty easy to understand because we use them as humans. You know, if we're lining up for something, whoever's been there the longest gets served first. So that's just a thing that we do as people, but we can do that for programs as well. So we can put a whole bunch of data in a queue and say that we need to process this thing in order. So the order that the stuff went into the queue is the order that it then gets processed. So that's what we say first in, first out. So the first thing that got put into the data structure is the first thing that gets removed. But a lot of the ideas that we would use is the same. So we can see that our abstract data types have this kind of rule structure around how something works. But underneath, we can make other things. And so there's lots of other different abstract data types we can make. So that's it for today. You will see things like abstraction a lot in programming. So I want to say that the ADT, the abstract data type, is just a C implementation of this. In other languages, you will definitely hear about these things called classes. So classes are an extension of this idea of abstraction, and they build up a bigger idea into this thing called object-oriented programming. You will see a little bit of that in the future, depending on what kind of programming you end up doing. Object-oriented programming, I want to say, appeared in, I don't know if it's the 1980s or earlier, and was very, very big in the 1990s. And I think it still had a lot of use in the first decade of this century, but it's starting to fade a little bit now. There are other forms of programming that are being used instead of it, because it had very good uses. Like, you can see how the abstraction is really useful. But a lot of the other stuff that's packaged up with it is starting to be used less nowadays. But you will still probably see a little bit of it. You'll see classes and object-oriented programming a little bit. This kind of leads us in that direction. Okay, so I should wrap it up there. We've got our code. I will upload the code. I'll upload both versions as well, so you can see the linked list partial implementation and the array partial implementation, so you can see how they both work. And you can see how either of them can hook into the header file and still be used from the same main that won't know the difference between them. All right, thank you very much, everyone. I will wrap up the lecture here. I will just switch to break mode, and I'll be back in a second and answer any questions people have about what we're doing at the moment. All right, I'm back. I realized that I started the lecture today. I don't know if you can see when I'm drinking, but I started the lecture today with like this tiny little 1 centimeter water in the bottom of my cup. And I was like, that's gonna hurt. And I started coughing by the time I got to the second half, because I didn't lubricate the voice box enough while I was talking. It's one of the funny things about lecturing is when I started out teaching, I didn't realize, but lecturing is like this really, really intense 2 hours of like just deliver lots of information, and I didn't realize that there's also physicality involved in that. Is like, maybe I should be doing like vocal warm-ups like singers do when they're performing and stuff like that before I lecture, so that I can actually like get through the 2 hours without starting to cough or anything. So it's pretty funny, I think, in the second half where I was like, bleh. Okay, do we have any questions about abstract data types or about the implementation that I did with the stack or anything like that? Feel free to throw your questions in the chat now, and I will answer them. Gira-chan, my rap is my warm-up. I haven't rapped in a while. I need to actually... I think it's also because this week, I don't know if anyone is so keen that you're watching my lectures from last term or the term before, but this week I've changed things. I used to do 2 lectures of abstract data types, but I realized that we don't need 2 lectures of abstract data types. Like, 1 lecture is enough to show the concept and how it works. So I was able to squeeze in another topic. So you're the first term this year that's getting this bonus topic called Recursion that's happening next lecture. So I haven't written a rap because I've been too busy writing new slides. Like, I was putting the ADT slides into one lecture and then writing the new Recursion slides that we're going to have on Friday. So Friday you're going to get a completely new set of slides that no one's ever seen before, which is going to be fun. It'll be fun, or either it will run entirely over time or under time, because when I haven't tested the slides, I won't know exactly. But I think it's an interesting topic. It's not necessary for the course. You can do everything in the course without it. But I mean, end of week 9 is a very bad time to introduce something that people definitely need for a course, because you've barely got one tutorial and no weekly tests to really wrap up that information. So that's why I put stuff which is like, this stuff is going to be potentially useful in the future and will lead on to other things, but you don't necessarily have to use it in 1511. I mean, I probably put some stuff in the exam that asks some kind of theory about abstract data types or something like that, but I won't necessarily say this is core. You know, like where I'm going to say linked lists is like super core to the course. You have a major assignment which is entirely about linked lists. Roughly 50% of the exam, the marks available in the exam will be based just on your ability to use linked lists. So it's going to be those parts of the course that you can consider important. But the stuff I'm doing this week is a little bit more of like it's still important. It's like vitally important for being a programmer, but not necessarily assessed right here and now in 1511. Yes, Gira-chan, you are the guinea pigs for my new lecture slides. I mean, think about the possibility of having, if you had started 1511 in term 1 last year, which was my first term teaching at UNSW, so 2019 term 1, that term were entirely guinea pigs. So all of the slides were new for that term, as opposed to after that, where only a little bit was different each term as I slowly iterate. And I deliver a lecture, and afterwards I look back and I say, I think maybe there was too much content there, or that didn't deliver the content the way I want it to be, and then I'll edit it and stuff. So the first term was just like, just make slides for the entire course. So that was that made that term entirely guinea pigs, but they seem to like it, so I guess that's okay. So Trent's asking, what's the difference between recursion and dynamic programming? Off topic, but that's okay. We're off time at the moment, so I'm happy to ask those questions. So recursion, I think maybe, have you done recursion before at all, Trent? Because recursion involves functions looping back on themselves, in a sense, whereas dynamic programming isn't necessarily functions looping back on themselves, but it's the idea of propagating your processing across a data set, in a sense. So dynamic programming can definitely be done with recursion, and I think that one of the best ways to do dynamic programming is recursion, where you will propagate across a data set and then have the information flow out and back in a sense. Because I think of the way I always think of dynamic programming is one particular example of it, where you have a 2D grid and you go starting from this square, show us the distance to like the other edges. So it propagates outwards until it hits the other edges, and then the data back flows, and then when you get all the way back to the beginning, you've got all the information from all the other things. And that kind of like propagation backtracking, I think, I haven't done dynamic programming in a long time, but that's like one of the ways that you do dynamic programming, and it works really well with recursion, because recursion says keep doing stuff until you hit something, and then like return through all of these functions as you go back. So I think the reason why they're kind of conflated is that they're used together a lot. But having said that, the what's I gonna say? There's a lot of recursion you can do that is not necessarily dynamic programming. I'm going to actually have to go back and Google exactly what dynamic programming is, because I'm not sure if what I've said there is the proper definition of it. It's been many years since I used it, but I have used it. Yeah, so hopefully that answers your question a bit. After we do recursion, you'll see that recursion can be a lot simpler than the idea of like what we're thinking about dynamic programming. All Night is saying, oh no, recursion nightmares of Python resurging. So yes, recursion is a I have slides about that. I haven't finished them yet, but I've got a couple of days before I'm gonna need them. But recursion's funny because it's like, if you understand recursion, it was good that you understood recursion, and it's good that you now understand recursion, and then I will teach you about recursion. Because that's how recursion works. Recursion kind of thinks about the finishing point, and then goes back through the ideas of how to get there, and that's how it runs. And so it's kind of funny that like it's nearly, you think about it the same way that it runs. Is it's a really weird concept, but once you get it, then you knew it all along. So it's just, yeah, you'll see on Friday. I'll talk about it. But what I'm gonna do is try to teach it in a way that builds up the idea of what it is. So I've actually sown the seeds already today. So today I was like talking about stacks, and that's very important because recursion and the program call stack are very, very interlinked. If you think about it, recursion as a stack, it's actually a little bit easier to wrap your head around it. So I thought that this week would be really good. So I'll teach stacks as a segue from ADTs into some of the theoretical capability that you need to understand recursion. So hopefully this week has a nice overarching narrative where the lectures aren't just separate topics, they kind of feed into each other like that. Looks like we don't necessarily have any questions today, which obviously means that the code I was writing was so good and so well put together that it was easy to understand, and everyone's getting the grasp of abstract data types now. Hopefully this is working, because like, as you notice, like I introduced multi-file projects, and I had to do that, right? Because like we're about to release an assignment, so I did not want to drop a multi-file project assignment on you without mentioning it. But I think that meant that when I was talking about abstract data types today, a lot of the ideas were already familiar because I talked about it in multi-file projects. Yeah. So it's looking like everyone's pretty happy with what's going on at the moment, so I might wrap it up there. Thank you for coming, and I will see you all on Friday with some fresh new content. Gonna drop some fresh tracks, and they're gonna be thinking about stacks, and you're gonna get programming to the max. That's what you get when I'm actually freestyling. That's how slow my brain actually works for rhyming things. Okay. See you all on Friday.